Hi, everyone, and thank you for coming. Today, authors Jorge Cham and Daniel Whiteson will be telling us everything they do not know about their new book, We Have No Idea. Jorge Cham is the creator of the popular online comic Piled Higher and Deeper, also known as PhD Comics. He earned his PhD in robotics at Stanford. Daniel Whiteson is a professor of experimental particle physics at the University of California Irvine and a fellow of the American Physical Society. He conducts research using the Large Hadron Collider at CERN. Please take a moment to silence your cell phones and anything else that will beep. And then join me in welcoming Daniel and Jorge.
Hello! Hello! How's it going? You guys don't sound very excited. I'll try. Yeah, all right. Not much better, but we'll take what we can get. Well, first of all, thank you to Google for inviting us here today. We are very excited, and I will tell you exactly how excited I am. But Google probably already knows everything about me, so there's no reason to tell you. Cool. Well, my name is Jorge Cham. As was mentioned, I'm a cartoonist, and this is Professor Daniel Whiteson from the University of California at Irvine. And together we're the co-authors of this book called We Have No Idea, which is about all the things we don't know about the universe. Now, today I'm going to talk to you a little bit about how our collaboration started, how we got together and wrote this book. And then Daniel will take over, and he'll talk to you actually about what's in the book. Now, I'm a cartoonist. And to me, being a cartoonist is about taking a blank page and filling it with an idea. And so the idea we want to draw out for all of you here today is this idea that there are still big gaps in our knowledge of the universe. Now, in addition to being a cartoonist, I also happen to have a PhD in robotics. Now, you might be wondering, what does having a PhD in robotics have to do with being a cartoonist? Well, I can tell you that my parents were also very concerned about that whole life plan. But I have a PhD in robotics from Stanford, actually, just down the street. And in fact, my research there focused on making robots that could run and walk like animals can in nature. And in particular, I focused on making robots that could run like cockroaches. Yeah. So here's a quick movie of what these robots look like. Yeah, so I like to show this movie at all my presentations for two reasons. First of all, I feel like this movie really kind of represents what getting a PhD feels like. Right, some of you might know the feeling. You feel like you're running frantically the whole time, but you're not getting anywhere. Meanwhile, there's a more intelligent being stamping you down the whole time. No, but I also like to show it because it's really kind of the only way that anyone will look at my research. Gotcha. Because it seemed that a little bit more popular than the research I spent years working on as part of my actual career, a little bit more popular has been what I was doing when I should have been doing research, when I was procrastinating, which was to make these comic strips called Piled Higher and Deeper, or PhD comics. Now, these are comics that I just started writing as a graduate student. It was my first year at Stanford, and I kind of wrote about what it was like to start in a PhD program and find a place in a lab. All the begging you have to do. I also kind of wrote about what it's like to be a teaching assistant. Right, dealing with those annoying undergraduates. We don't have any here today, do we? Any interns? No? Oh, all right. I'm sure you're cool. Sure, you're here, you must be cool. Let's see, the comics were also about learning about grad student etiquette. What you should never ask a grad student. How's your research going? Cool, so I just kind of kept drawing these comics, and then one day I decided to take my procrastination to the next level. And I started posting these on a free web server on campus. And as most things like these happen on the internet, you know, somebody read it on campus and liked it, and then they told their friends that they knew in other universities about this website, and then they told their friends and their lab mates, and those people told other people in other universities. And so slowly over the years, these comics kind of spread out into the world, kind of like a virus. To the point where about 6 or 7 million people a year come to the PhD Comics website, which is an incredibly small number. If you think about the fact that there are about 7 billion people on this planet, so there's about a 0.1% chance that you've ever heard of me before I walked into this room. But it just so happened that one of those millions of people who went to the website was a professor at the University of California at Irvine, who saw these comics, and he decided to email me one day. Out of the blue, I just get this email in my inbox saying, "Hey, Jorge, I've seen your comics online. I think they're pretty good. Can I commission you, can I pay you to write some comics about the Higgs boson?" Now, this was a few years ago where there was a lot of attention in the media being paid to this discovery that people were searching for the Higgs boson. And Daniel, the professor, didn't think that people were doing a good job of explaining what this interesting and complex phenomenon was and how people were looking for it. So he decided to contact me and offer to commission me to make something that explained what it was. And so I thought, what? You want to pay me? What is that? I don't understand. I just put things on the internet for free. So I said yes, and so I went down and I interviewed him, and we had a conversation over lunch at the cafeteria. And instead of taking notes, I kind of brought my recorder and I recorded our conversation. And then when I went home to draw these comics, I decided to experiment a little bit. And so I took the audio from the recordings and I recorded myself drawing the comics, and I kind of put those things together, and we made a video in addition to the comics. And we decided to take this video and we posted it on this website. You may have heard of it. It's called YouTube. And so now I'll just play for you guys 1 or 2 minutes clip, a 1 or 2 minute clip from this video, just so you kind of get a sense of how our collaboration started. So here's a clip from the video.
One of the things people predict is the Higgs boson. The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? Mm-hmm. Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons. Some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Right. Interestingly, you can't have negative mass or repulsive gravity. So the collision happens. It lasts for like 10 to the negative 23 seconds, and you get one measurement, right? So if you say, well, I'm going to plot the mass, the total energy of this guy. I'm going to add this guy and this guy together and add the total energy. This is this axis here is number of collisions. You do an individual experiment, you get one measurement, right? Here. You do another one, you get another measurement. You do another one. Eventually you build up your data, right? And the data looks like this, for example. And then you have two theories, right, that predict the data. One says, well, I'm going to predict there's no Higgs boson, so the data should fall along this line. And the other is I'm going to predict that plus a Higgs boson. And the problem is the difference between these two theories is very small. And so it's very hard to distinguish these two with our data because the predicted effect is tiny, right? If the predicted effect were huge, it'd be very easy to tell the difference between with Higgs boson or not with Higgs boson. But the predicted effect is tiny, and so it's really hard to see. What you need is a huge amount of data. You need to take a bajillion collisions before you can see the difference. That's why we run this thing 40 million times a second, all day, all year, to get a lot of collisions to tell small differences between theories. It's like when you take a picture of the sky. If you just take a picture, you get a little bit of light. The longer you leave the telescope looking at the sky, the more you can see farther away things.
I like it. Cool, that was the video. And so we posted this online. And then it just so happened that a few months later, they actually discovered the Higgs boson. And so when they discovered that there was a huge amount of attention paid on this from the media and the popular press, And this video sort of went viral. Millions of people watched this video, and a lot of people were pointing to this video as the clearest and easiest to understand explanation of what this kind of complex phenomenon was and how people were looking for it, and why, especially why they were looking for it. So I thought that was pretty cool that, you know, the clearest and easiest to understand explanation didn't come from the New York Times media department. It didn't come from some, professional company or animators. It came from actually one of the scientists who worked on the project, who decided to take the initiative and commission an artist to work with them to create something that explained this to the public. So I thought that was pretty cool. So since then, we've worked on a couple of other projects together, but our latest project is this book called We Have No Idea. And now to talk to you about the ideas inside of We Have No Idea is Daniel Whiteson.
Hello, everyone, and thanks, Jorge. So before I get started, I have to correct Jorge's story a little bit. He's overly modest when he tells that anecdote. If any of you have been in academia, then you know that Jorge is not just a cartoonist, he's sort of a celebrity. I go around and I visit lots of physics labs, and on almost every single wall there's one of Jorge's cartoons, because he's really captured the suffering of the graduate students. So he's really super well known. And when I was thinking about how to explain physics using cartoons, I thought, well, who could possibly have both the artistic skills and the technical understanding to communicate these difficult topics, right? And so my wife, who's also a huge fan of PhD comics, said, why don't you email Jorge Cham and ask him to do it? And I thought, sure, yeah, and then I'll write an email to Brad Pitt and ask him to make a movie about me also, right? Like, just as likely to be successful. But Brad hasn't gotten back to me about the movie, but I had the great pleasure of working with Jorge on this project. Yeah, you're Brad Pitt in this scenario.
I like it.
Yeah. So our book is called We Have No Idea. And instead of being another science book that explains what science has figured out, the focus of this book is about what we don't know, all the things that we don't know about the universe. So if you come to hear a talk from an author, you expect them to be an expert on the topic, right, a real authority. So you might be wondering, well, like, what's this guy's expertise, like not having ideas or something? You know, and so it doesn't sound so great to claim that I'm an expert in our level of cosmic ignorance, but that's sort of the situation. And you might wonder, well, why write a book about the things we don't know? And it's not that I want to celebrate our ignorance. There's plenty of that going on already. It's that I want to convince you that in science, ignorance is opportunity. It's an opportunity to make discoveries, because when you know what you don't know, then you know where to look and how to answer these questions. Okay? And so what I want to do, and what we hope to do in this book, is to introduce you to our staggering cosmic level of ignorance, to prepare you for all the awesome discoveries that we think are coming around the corner. Okay? Because it's when you can confront your ignorance, then you know how to look for the answers, you know how to begin your exploration. In the end, it's really about the exploration. And when I was a kid, I thought the age of exploration sounded like a lot of fun. I mean, all you had to do to discover something new back then was jump in a ship, sail across the ocean, and land on a new beach, right? You could be the first person to ever walk on a beach or eat a new kind of fruit or something, right? These were amazing firsts in human history, and I wanted one. You know, imagine like the first person to ever see the Grand Canyon, right? There was a first person that got to do that. Or the first person to ever eat chocolate, right? That was an experience. Or the first person to ever eat chocolate while looking at the Grand Canyon, right? These are all important firsts in human history. And I wanted to be the first person to know something or do something or see something, right? But as you're reading about the age of exploration, this happened hundreds of years ago. You know, there aren't any more new continents to discover or islands to land on and name after your poodle, right? And thanks to, you know, Google Earth, for example, it's very difficult to say that there's anything left to explore. And the more you look around you, the more you get the feeling like, well, not only have we explored and mapped the surface of the Earth, we've also really started to master technical things and the way things work, right? I mean, we have amazing things, airplanes that can fly over oceans and can download all of human knowledge into a little device that fits in your pocket, right? You know, you can make $1 billion off of a single idea. I mean, it's truly a crazy modern world we live in. It's an age of wonders, okay? So you might get the sense that science has mostly figured things out, that we just have a few little details to wrap up and then we're basically done understanding the universe. Well, the point I want to make to you today, and the point in our book, is that exactly the opposite is true. that in fact we're at the beginning of a new age of exploration, an era of exploration that I hope will reveal staggering, crazy ideas about the universe that currently we have no idea about. Okay? So what do I mean age of exploration? Like how is it possible to explore things where we've had such a deep understanding of the universe? Well, the kind of exploration I'm talking about is the kind where we ask big questions, okay? Really big, fat, juicy, basic, ancient, deep questions. The kind of questions that everybody wants to know the answer to, right? The really big, fat questions. The questions which, if you knew the answer, it would change the way you felt about your place in the universe and the human situation, you know? These kind of big questions. All right, so let's be concrete about it. What kind of questions am I talking about? Well, you went down the hallway and asked a random person, what are the most important questions in life? They might say things like this, right? Well, why are we here? That's a big one, right? What happens after we die? Also an important question. If I knew the answer to that question, it might change the way I live my life or treat people, right? These kind of really deep, big questions. Another popular one is, what is it like to be a bat, right? This is a question people think about sometimes. And the interesting thing about these questions is that while they are deep questions and important questions, they're also philosophy questions, which means that you can spend a lot of time thinking about them and arguing about them and not necessarily make any progress, right? Even if you smoke banana peels for 20 years and go down to the philosophy department, you might not figure it out. And you might think this last one, what is it like to be a bat? You might think that's just a joke. It's actually the title of the most widely cited philosophy paper of all time, okay? People are still arguing about what it's like to be a bat, and I think they're never going to figure it out. And that's the problem with philosophy questions. They're important, they're deep. I don't mean to dismiss philosophy, but they don't have objective answers, okay? The cool thing to me is that there are other questions just as deep, just as ancient, just as important, but these are science questions, okay? Questions like this: what is everything made out of? How did the universe begin? Okay, the universe has one true history. It began in a certain way and no other way. And if you knew that story, here's how the universe began. Here's what came before the Big Bang. Here's what caused the Big Bang. You would feel differently about about our lives and the way we live it in the future, right? These are important questions at the same level. The cool thing is these questions have answers, right? There is a true factual answer to these questions, and we can discover it. If we do the right experiment and put together the right pieces and the clues, we could actually learn the answer, after which, no matter how many banana peels you smoke, no reasonable people can disagree anymore about the answers, right? Unfortunately, we can't include like the US government in the list of reasonable people anymore because they don't listen to science, but you know, people who listen to science and accept objective truths can actually agree on the answers to big, deep, and ancient questions. To me, that's incredible. And that's the kind of exploration that I'm talking about. Okay, so let's zoom in on one of these questions. This one here is the one that I spend my professional life working on. What is the universe made out of? And this is really a basic and a reasonable question. I mean, if you wake up as like a conscious being in the world, you look around you and you ask, what am I made out of? What is he made out of? How does everything put together? What are the rules, right? What is the most basic element of matter? How does this whole thing work? It's an ancient question, a basic question, and I think a reasonable one to want to know the answer to. I remember as a kid smashing rocks together and seeing them break into smaller rocks and wondering, how long can you do this for, right? Can you just keep getting smaller and smaller rocks? At some point, is it no longer rock? And I imagine that people have been doing this for a long time. I don't think I'm the first person to ever smash rocks together, right? I think it's an old question. It's the kind of question people have been asking themselves since people have been asking questions, right? And if if particle physicists were superheroes, this would be their origin story, right? Something like this. This is the dawn of particle physics here. Okay, and it's an important question, but it's a difficult question to tackle, right? What is everything made out of? It's a big question. How do you approach that? Well, in science, our strategy when we are tackling something very big and very difficult is try the dumbest thing first. Okay, just do the simplest, most obvious thing first. That doesn't work, try the second dumbest thing or extrapolate from it a little bit, right? So what's the simplest approach to answering this question, what is everything made out of? Well, you might just try a list, right? Look around you and literally say, what's in the universe, right? Okay, so your list might look something like this, right? The universe has me, it has you, it has this rock, the other rock, that other rock over there, right? And this approach using a list is going to have a lot of problems, right? Problem number one is the universe has a lot of rocks in it. So your list is going to be super duper long, right? And you guys like thinking about lists and organizations. You might also wonder like, well, is the list exclusive or inclusive? You know, because if it's inclusive, then I have to have all the things in the list also, and there's a list on the list. You know, lots of problems there.
The other problem with the list approach is that their universe has more than just rocks in it, right? For example, as you look around you, you discover the universe is full of all sorts of crazy, interesting things, right? There's rocks, but there's also air, and there's water, and there's fire, and there's blueberries and iPhones, right? And the more you look around, the more you're sort of impressed and staggered by the incredible complexity of the world we live in, right? For example, there's puppies and bicycles and strangely muscular fellows who become governor of California, right? The world is really full of interesting stuff. And that's one of the things that makes it a nice world to live in, right? You wouldn't want to live in the world that's just rocks, right? For example. And it also highlights what's a problem with this approach, right? Is that the list isn't really an answer. If you asked me, what is the world made out of, Daniel? And I literally gave you a list that had everything in the universe on it, that wouldn't really feel like an answer to your question, right? It's like asking a teenager, where are you going? And they say, out. Okay, well, it's an answer, but it's not really an answer to the question, right? It's not a satisfying answer. So what kind of satisfying answer would you like? You'd like something that reveals something about the world, something that explains all this incredible complexity in terms of something simpler, right? You want to peel back a layer of reality and reveal the simpler set of building blocks that explain all of this complexity. So how do we do that? Well, we have this dumb list, right? So let's try the second most dumb approach, which is organize our list, right? So we categorize things and we say, well, this stuff over here is all rock-like, and this stuff over here is plant-like, and you can argue whether Arnold belongs in the rock category or the living thing category, right? Everything belongs in a category somewhere. We're scientists about it. And you start to notice patterns. So you make a list, you organize it, you notice patterns, you ask questions about those patterns because those patterns are your clues. They're the roadmaps that tell you what's going on underneath. Why are there so many rock-like things? Why are these things all similar, right? There must be some pattern there. Okay, so we've done that. And fast forward a few hundred years or a few thousand years, depending whether you give the Greeks any credit for this kind of stuff, and you get to the periodic table of the elements. And you guys might be thinking, we're smart people. He's a particle physicist. Why are we talking about high school chemistry, right? Periodic table is high school chemistry. Well, it is high school chemistry. It's also, in my view, one of the most staggering achievements in human intellectual history. Why? Because it's taken us from an almost infinite complexity of stuff down to 100 building blocks. From those 100 building blocks, you can make anything that you've ever touched or tasted or driven over or anything, right? Anything any human has ever interacted with has been made out of these 100 building blocks. If our goal is to simplify the universe or reveal a simpler nature underneath, this is a huge step forward already, right? And this is hundreds of years ago. So it's sort of incredible. And it makes you wonder, like, why is it even possible? Why is it possible that why do we live in a universe where it's possible to describe complexity in terms of simple stuff, right? It means something deep. It means that all that complexity is in the arrangements, right? Not in the objects themselves. It reminds me of something else, right? It's like the universe is organized by the Lego principle, right? That out of a few basic building blocks, you can build anything. You can use the same basic building blocks to build dinosaurs, right? Or to build pirates, right? Or like dinosaur pirates, right? It's incredible that anything can be made out of these building blocks. And to me, it's interesting because it seems like if you were caveman or cavewoman physicist, right, and you were asking this question for the first time, you might consider various options. Maybe the world is not made out of basic building blocks. Maybe it's infinitely divisible into smaller and smaller pieces using an infinitely sharp knife, right? Could have been. Or maybe instead of having a simpler small set of building blocks, maybe the number of building blocks could have mirrored the number of things, right? And you could have had, for example, cats made out of cat particles, and cartoonists made out of cartoon particles, and llamas made out of little llama-linos, or whatever you'd call those particles, right? That certainly could have been. And if you're the first person to ask this question, you have to consider every possible idea because you have no rules about how the universe works, right? But nothing that you see around you is a basic building block of the universe, right? And we don't just list the periodic table of the elements and say we're done, right? We don't just list the elements and say we're done. We organize our knowledge, right? So we group it into the periodic table of the elements. After all, there are patterns here. That's why we call it the periodic table of the elements. Okay, I can see Jorge is getting bored because he's playing Tetris here. But there are patterns here, right? And if our goal is to reveal one more layer of truth, to reveal the simpler structure that underlies it, we have to look for patterns. And so I'm not a chemist, but I know that in the periodic table, these guys over here on the right side are not very active, and these guys over here on the left are very active. In the middle, you have these metals, right? and all sorts of stuff. And there are patterns in the periodic table. And these patterns are, in fact, the clues, right? They tell us what's underneath the periodic table. And we know now, of course, because we've all taken high school chemistry, that all the patterns in the periodic tables are just emergent phenomena from the structure of the atom, right? They were, in fact, clues that pointed us down to reveal what the nature of the atom was. And, you know, the reason that these guys are noble and these guys are not noble and the metals are the way they are is because of this structure. It's because the electrons fill up their orbital shells and don't like to play games anymore. It's because the number of protons in the atom determines the element that you are. So all of the chemical properties are just clues that pointed to the structure of the atom itself, right? And so we can look to those clues to tell us how to understand a deeper level of reality, right? Down below the hula hoop level. Okay, but remember, as we're exploring the universe, that nothing that you know is a building block of the universe. Nothing you've played with. The chairs you're sitting on, the llama you rode to work on, right, the tornadoes, none of these things are basic building blocks of the universe. The universe is built out of deeper, weirder, strange things that have no analog in your life, right? Not even strange combinations of things like llama tornadoes can explain the way the universe works. You know, we like to use intuitive ideas like particles, which are little spinning balls, or waves, which we know about from things, or maybe light is a particle and a wave, right? In reality, the basic building blocks of the universe are totally alien to us. We can try to understand them using these analogies, but in the end, they don't really work. Okay, so let's zoom in a little bit and understand the current state of knowledge. All right, we have the atom, which has protons and neutrons with electrons whizzing around it, of course, right? And inside the proton and neutron are quarks. So you have the up quark and the down quark. You put two up quarks and a down quark together to make a proton, two down quarks and an up quark together to make a neutron, right? And that means something sort of astounding. It means with just these three particles, up quarks and down quarks to make your protons and neutrons, and then electrons to complete the atom, you can build any atom. Any atom can be built out of three particles, and anything can be built out of atoms, which means anything you've ever tasted or stepped on or interacted with can be made out of just three particles. That's incredible simplification, right? From infinite complexity down to three particles. It means the recipe for building literally anything is certain number of up quarks, certain number of down quarks, electrons, mix, right? That's literally the recipe for everything. In terms of simplification, that's pretty impressive. So you might be thinking, wow, we went from infinity to 100 to 3. We're like on the verge of figuring this out, right? The trajectory is pretty good. If these guys had come next week, they'd be showing us the one particle that rules them all, right? So we're not quite there. And the point of the book is to explain to you the wrinkles in this story, because the wrinkles are really interesting. Okay, so first of all, one wrinkle is we don't just have these three particles. We found these three particles, but there are more particles. Okay, the up quark and the down quark are two examples of quarks, but there are other quarks. There's the charm quark, the strange quark, the top quark, and the bottom quark. Okay, I'm not making these names up. Okay, I wish somebody had asked me. I would have come up with even sillier names. The electron is an example of a particle we call the lepton, and there's 6 of those as well. Okay, so we have not just 3 particles that make up matter, we have these 12 particles that we've discovered. So what do we do in science when we're confused, we don't know what to do? Well, first we just make a list, then we organize it, right? So now the current state of knowledge is this, a new periodic table. It's a periodic table of the fundamental particles, right? And what we try to do is place all these particles in a table so we can understand how they fit together, maybe get some clues which will lead us to ask questions that will reveal an even deeper layer of the universe. So we have the up quark and the down quark, which you know. These make the protons and neutrons. Together with the electron, they explain everyday matter. But in this first column, we also include this particle called the neutrino. Neutrino is a really strange, mysterious particle. It's sometimes called a subatomic particle. That's not really accurate because it's not inside the atom. But it's a mysterious particle, but it's also everywhere. For example, there are 100 billion neutrinos passing through my fingernail every second. 100 billion, and your fingernails as well, right? So why are we not like getting beaten down by all of these neutrinos? Is they pass right through us without even noticing. We don't notice them, they don't notice us, right? It's like that guy who lives down the hall from you. You don't even like make eye contact, right? Totally just pass right through each other. So neutrinos ignore us and we ignore them. There's so many neutrinos because they're being produced by the sun. But it's a clue that a lot of the things that are happening in the universe all around you, you're not privy to. You can't see, you can't immediately detect. Okay? The universe is different from the universe that you experience. So we put all these 4 in the same column. And the interesting thing is about the 12 particles is that there seem to be copies of each other, right? So for example, the charm quark and the top quark, we put them in the same row as the up quark because they are copies of the up quark. They have exactly the same properties, the same charge, the same interactions, the same spin. All these things are the same, except the charm and the top are heavier than the up quark. Okay? Why are they there? Why does the up quark have these like weird two secret heavy cousins, right? Nobody knows. The charm quark is much heavier than the up quark. The top quark is the heaviest fundamental particle we've ever discovered. It's thousands and thousands of times heavier than the up quark. It's like the up quark's secret fat country cousin that can't even leave the house, right? It's like shin-snappingly fat, this one. It's also easily offended. So the fascinating thing is that not only are there two copies of the up quark, there's two copies of the down quark. The strange and the bottom have the same relationship. They're perfect copies of the down quark, all the same properties except heavier, right? The electron also has these copies. There's the muon, which is just a heavy version of the electron, and then the tau, which is an even heavier version of the muon. There's even 3 of these neutrinos, right? So we have these really interesting patterns that form when you start to organize our knowledge of the periodic table of the fundamental particles. What does it mean? Well, I hope that it means that there's something deeper going on. Currently, we have no idea, but we have some fun questions, right? The patterns give us questions, and we hope those questions will lead us to the answers. Okay, so what questions do we have? Well, question number 1, why do we have all these particles? You only need 3 to make all of matter, right? Why 12? Are there in fact 12? Are there 24? 24 billion? According to theorists, there's no limit on the number of particles that you could have in a fundamental theory, right? How many particles are there? Why do the particles each have 2 copies? To me, this is a really interesting, deep question because I like thinking about numbers, right? One of the fundamental goals of physics is to explain the whole universe in a simple equation. How do you know when you're done, when that equation is simple enough? Well, the standard people often use is if it could fit on a t-shirt. Okay? If you can put all of physics on a single t-shirt, then you're done. Imagine we were there and you're looking at that equation and there's a number in it, right? 5. That means that 5 is a deep, important number somehow in the universe, right? All right, so numbers are important. Now we look at this table, we see there's 3 copies of every particle, right? Why 3, right? If you ask theorists and mathematicians, what kind of numbers do you expect in a fundamental theory? Oh, they have strong opinions, right? 0, that's an okay number. 1, you can have pi, sure, pi is a good number, right? Nobody says 3, right? Unless they're Catholic also, right? Like, why is 3? Is the number 3 somehow important to the universe? It seems to me like either it is or it's a clue, right? That in 1,000 years or 100 years, people are going to look back and say, that was such an obvious clue that blah, 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 whatever secret of the universe hasn't been revealed to us yet, right? It's staring them in the face. If I had been a physicist then, I totally would have figured it out, right? It's one of those screaming clues that we just don't know what it means right now. We just know it's a clue, right? Another big mystery about these particles is the relationship of the masses. We know that in general they tend to have more mass as you go this direction, but there's no pattern to the masses. The Higgs boson, if you know anything about it, explains how the particles get mass, but it doesn't tell you why this one got a lot of mass and this one got almost none, right? There's no explanation for that at all. And the ratios are crazy. The top quark is thousands of times heavier than any of the other particles. It's really strange. But one of my favorite ones is this one about the charges of the particles. So the electron is charged -1, sort of by definition. But the quarks have these really strange fractional charges, like 2/3, -1/3, right? How is that even possible, a fractional charge? Well, that's just because of how you define the charge of the electron. But the interesting thing is about the ratios. These guys add up 2/3, 2/3, 1/3 to make +1, a proton, which perfectly balances the electron, right? Well, that's convenient because you need that exact balance to have neutral atoms and to have physics and chemistry and biology and silly physics books and free lunch in the cafe, right? All that stuff rests on this perfect balance. But in our theory, that's a perfect coincidence. We have 2 knobs in the theory, the charge of the electron and the charge of the quarks. If you're at the control panel of the universe, you could set those things to be anything and you still get a valid theory of physics. So why do they balance perfectly? Well, either it's a huge monster cosmic level coincidence and not an almost coincidence like the moon and the sun being the same size in the sky so you get an eclipse, but a perfect exact coincidence. Okay, that's strange, right? That's a clue. But in our current theory we say, no, there's no relationship, right? 2 arbitrary numbers. To me, it's possible that there's a simpler explanation, right? That these things are actually built out of the same smaller set of Lego blocks, which would explain why they have a perfect balance in their charges. But currently, we have no idea what that explanation is. And we don't just like thinking about how, the particles, we also like thinking about how they talk to each other, right? The forces they feel when they come into play. And before Jorge was the favorite cartoonist for particle physicists, we had Richard Feynman, who came up with the Feynman diagram, sort of a cartoony way of thinking about physics. And he thought about the way particles interact with each other by drawing these diagrams. And so the straight lines are particles moving, and the wiggly lines are particles talking to each other. And we can use his calculations in this strategy to predict the results of experiments. And if you've ever worked in an experimental lab, you know that if you predict an experimental result and you get within like a factor of 2, you're like, wow, it works, science, yay, it's amazing. Well, we can predict the results of experiments and get the results to agree with the theory to 10 decimal places. 10 decimal places. It's incredible precision. So the theory we have about how the particles talk to each other works super duper well, right? It almost makes you think, if you're a conspiracy theorist, that like maybe we are living in a simulation and we've like uncovered the source code of the universe, you know? Maybe this is how the universe does the calculations to decide what an electron is supposed to do, right? Because this doesn't happen by random, that you get this level of agreement. By random chance, it'd be like hitting a golf ball in New York and getting a hole-in-one in China, okay? It just doesn't happen by chance. But we don't measure our particle theory just by how well does it work, like does it predict experiments. Remember, we want a really simple theory. We want to simplify the universe. So let me show you the current state of the art in thinking in particle physics. This is the Lagrangian that describes the standard model of particle physics, okay? And you know, in my estimation, it doesn't quite yet fit on a t-shirt. In fact, only half of the terms could fit on the screen. So we're not quite there yet. We have a lot of questions left about how these particles talk to each other. But that's not the end of the story. That's not even the biggest problem in particle physics, right? So first I want you to go away with a feeling like, wow, there are deep, basic questions about how particles work that we don't know, right? We've made a lot of progress, but we're staring into the abyss. And we feel like in 1,000 years, people will look back and think, wow, those things were really obvious, or I wish they knew this, or how could they not have figured that out, right? Well, it turns out all of those questions are a tiny fraction of the questions we have about the universe. Because the particles I've introduced you to and the everyday matter that you're familiar with, and everything that makes up me and you and hamsters and stars and dust and planets, only accounts for a tiny fraction of the universe. All of that effort understanding matter only explains a little sliver of what the universe is actually made out of, right? So all that great progress, divided by 20. So it turns out that only 5% of the universe is this kind of stuff, right? So we've measured very precisely the fraction of stuff in the universe that's our kind of stuff, and that's 5%. The rest of it is a big mystery, right? The rest of the stuff in the universe, we don't really have any idea what this kind of stuff is. So it's an incredible moment in physics, a moment I call precision ignorance, when we've measured very precisely that we don't know very much about the universe. And that's exciting because it means we have a lot of things left to discover. So how is it possible that we could know that we know very little about the universe, right? How does that exactly work? Well, let me tell you a little bit about it. The first part of the story begins with galaxies spinning. So somebody sent their grad student out to look at galaxies and understand how they spin. And if you want to think about galaxies, a good model is to think about a merry-go-round with a bunch of ping pong balls on it. What happens if you spin that merry-go-round? Well, the ping pong balls are going to fly all out, right? Unless there's some force holding them in. So in the case of galaxies, that force is gravity. Keeps all the stars from flying out of the edge of the galaxy. So you can do something interesting, which is measure how fast the galaxy is spinning, and then count up all the stars and ask, is there enough gravity to keep all the stars in based on how fast they're spinning? So somebody sent their grad student off, make sure this works, make these two measurements, make sure they agree. And what they discovered is that the galaxies are spinning much, much faster than they should be able to. Galaxies spinning that fast should be throwing their stars out into space all the time because there isn't nearly enough gravity to hold them in when they're spinning that quickly. This was a really perplexing result for a long time. People didn't understand it, and they thought, well, maybe you mismeasured how the galaxies are spinning, or you miscounted the stars, or something is crazy. And then eventually people thought, well, maybe there's something else in those galaxies. Maybe there's some sort of new invisible thing, because we don't see it, that has a lot of gravity to it, right? So you need something that's invisible and has gravity. So they called it, they didn't know what it was, but they called it dark matter. And literally, dark matter is the name of the theory. It's also a summary of what we know about it, right? It's dark and it has matter. And that's basically what we know, okay? That's the idea. It's also what, was the problem it was trying to solve. Like, there must be some sort of dark matter-y stuff to explain all of this. So it was a big mystery for a long time, but if you postulate the existence of a huge amount of invisible matter in these galaxies, it explains why they're spinning so fast. But to understand how dark matter is dark, we have to spend a moment thinking about how particles interact. So we say dark matter is dark because it doesn't give off light, it doesn't reflect light, the way planets and stars do, right? That means it doesn't feel electromagnetism, which is one of the 4 fundamental forces responsible for light. There's also gravity, which anything that has mass will feel gravity, it'll attract itself. And then there's the weak nuclear force and the strong nuclear force, which are responsible for holding the nucleus together and also radioactive decay. So when we talk about dark matter, we know that dark matter feels gravity, right? Because that's how it was discovered. It basically, explains the extra gravity we need for the galaxies to rotate. We know it doesn't feel electromagnetism, because if it did, then we would have seen it, right? It doesn't feel the weak force, and it doesn't feel the strong force. And as far as we know, dark matter doesn't feel any other kind of force at all. We've been trying to interact with dark matter in lots of ways, but it never seems to respond, even to our Facebook requests, right? All we know about dark matter is that it feels gravity. It's sort of defined to be the thing that gives the extra gravity. And so 5% of the universe is the stuff we know that we still have a lot of questions about. The fascinating thing about dark matter is that you need a lot of it to explain how the galaxies are spinning. It's not like, oh, you need 1% or 2%, it's a little bit of a correction. It's a mammoth correction. You have to multiply the amount of matter in all the stars by a factor of 5 to get enough gravity to explain how rapidly these galaxies are spinning. It's a crazy idea, right? When we think of a new physics theory, we like simplicity, right? Think of the simplest theory that explains your data. Well, if your theory requires, an immense amount of invisible matter that permeates the universe that nobody's ever discovered before, well, then maybe you go back and check your calculations, right? Before you get that published. And it took people a long time to accept the idea of dark matter. In fact, it wasn't until people found other ways to see dark matter that they really became convinced it was a thing and not a mistake. One really cool way to see dark matter is to see it acting as a lens in the sky. So dark matter is invisible, which means light passes through it, but it has mass, so it bends space and it can bend light as well, acting like a lens. So imagine there's a huge blob of invisible dark matter between you and some far, far away galaxy. What happens to photons leaving that galaxy? Well, a photon zooming off in one direction will get bent towards you by this blob of dark matter, right? A photon zooming off in another direction also gets bent towards you. So what happens if you look out in the sky in 2 different directions? You see the same galaxy at 2 places in the sky, right? It looks just like a lens is acting somewhere in the sky. In fact, it's more than just duplication. It actually gets distorted, all sorts of interesting optical effects, just like you would expect from a lens. You can Google image search it later. It's pretty awesome. It's called gravitational lensing. And when people saw this, they thought, well, there must be some invisible stuff out there that really does have gravity to it. It's pretty spectacular discoveries. And then the last bit came from a collision. Now, I'm a particle physicist, so when I want to solve a problem or understand something, I smash stuff together, okay? That's like my modus operandi, right? Collide particles together, look to understand what's inside them. If you want to understand galaxies, that approach doesn't really work, right? You can't say, like, go to the government and say, I want funding to build a galaxy collider, okay? Even these days, we don't have enough funding for science. So we can't use all the science funding on a galaxy collider. So an astrophysicist has a different approach. Instead of building a collider, they just look out into space and hope to find this experiment already happening. And fortunately, they found one. So the bullet cluster is a mammoth cluster of mammoth collision of 2 clusters of galaxies. So a cluster of galaxies has both normal matter and dark matter in it. So what happens when these 2 things slammed into each other? Well, the normal matter smashed into itself, just like you'd expect when 2 planets collide in science fiction movies, right? Boom, boom, everybody runs away. But the dark matter passes right through the normal matter. Okay, it's invisible, it's also untouchable the way neutrinos are. And it passes through the normal matter, it also passes through itself. So it just passed through itself to the other side. So you get dark matter on either side, and in the middle you have these big explosions from normal matter. That's really cool because it means that the normal matter was separated from the dark matter. And you can use gravitational lensing to see directly that the dark matter is there, right? And the normal matter is still in the center. So this is a way you can separate the two. You can see that dark matter really is its own thing. It's not just a weird miscalculation of gravity or new theory of gravity for normal matter. It's its own new kind of invisible stuff. All right, so the bullet cluster really was the nail in the coffin for all the other theories that tried to explain dark matter and convince people that dark matter really is a thing. It's really out there. Okay, so what is dark matter, right? We know that it's dark, right? We know that it's matter. We know there's a lot of it. That mostly sums up what we think. You know, we don't know what it is. We know that there's more of it than our kind of matter. Now, we're particle physicists, so we're physicists, so our natural inclination is to explain the unknown in terms of the known. So, for example, one of the favorite theories about what is dark matter is, well, maybe dark matter is made out of particles, just like we're made out of particles, right? And the favorite theory is called a weakly interacting massive particle, right? WIMP. That's one of the favorite theories. Another one is, well, maybe it's these big blobs of matter out into space. It's called a massive astrophysical compact halo object, right? That theory is called the macho, okay? So even in science, we have the WIMPs versus the machos, right? These are two ideas, but they're sort of extrapolations from what we know, right? And it's dangerous to extrapolate to a quarter of the universe from a tiny, probably atypical sliver that you've been studying for hundreds of years. Right, so we should keep that in mind. And the other thing to remember is that dark matter isn't out there in the universe. Dark matter is everywhere. Dark matter is here in this room. Okay, I have dark matter in my hands right now. It passes right through us. I can't hold it or contain it, but it's here with us. It's not like out there somewhere. Maybe dark matter is a totally new kind of matter. Maybe it's not even made out of particles, right? Or maybe it's made out of a whole new kind of particles the way we are, right? Many different kinds of particles. So maybe this complex dark matter physics, and dark matter chemistry, dark matter biology, right? For all we know, there could be dark matter life right here in this room with us, right? And if you were dark matter life, you wouldn't think of us as normal matter, right? We're the little sliver 5% you could almost round away in your understanding of the universe. In some dark matter physics class, is a professor saying, yeah, we understand 96% of the universe except for this little weird sliver, right? So maybe there are dark matter tourists, right? So 5% of the universe is explained by the particles we have some clue about. 27% of the universe is dark matter, right? We know it's there. We don't know very much about it. That still leaves 2/3 of the universe's budget totally unaccounted for, right? No accounting firm is going to accept that. So what is the rest of this pie? Well, the rest of this pie is filled by something called dark energy. Okay, but dark energy is really science code for we are totally clueless, okay, about the rest of the universe. Because the truth is, and until 20 years ago, we didn't even know that we were clueless about this part. Okay, now don't be confused, dark energy and dark matter have no relationship other than literally the word dark. Okay, that's the only connection between the two theories. Okay, so how did people even figure out that dark energy was a thing? Well, people were thinking about the history of the universe, okay? So if you know something about physics, here's a brief summary of the history of the universe. Okay, so first you had the Big Bang, right? And all the stuff in the universe exploded out, and then, you know, interesting stuff happened. And people were wondering what's going to come next. So is there enough gravity in the stuff in the universe for things to slow down, turn around, and then come back into a big crunch? Okay, that was one possible explanation for the history of the universe, the future of the universe. Another possibility is that there wasn't enough stuff in that initial explosion, not enough gravity to turn things around. It would just drift out gradually, slowing down, cooling off, till the universe cools off and spreads out into something known affectionately as the heat death of the universe. Okay, not a cozy time. But these were the two possible theories that people were considering, the big crunch or the heat death of the universe. So they said, well, let's measure it. Let's go out and look, see if things are speeding up or see how much things are slowing down. So it turns out the universe preferred secret option C, which is neither of these ideas, right? Which to me is like the best case in science, when you discover something that nobody expected to be the answer, right? So they went out and they measured it, and they discovered that actually what's happening is that it's not slowing down at all. It's expanding faster and faster. It's accelerating in its expansion, right? That's crazy. Nobody even thought about that as an idea, because to accelerate the size of the universe requires some sort of force, right? Which requires some sort of energy. And the amount of energy that would be required, well, that'd be like 2/3 of all the energy in the universe, right? That would be totally crazy. In fact, that's what's happening, and we have no idea why. Right? We know that it's happening. We've measured it. We see that the universe is expanding faster and faster every year. We just don't know why, right? What could possibly be responsible for pushing galaxies away from each other? I mean, galaxies are heavy, right? Hundreds of billions of stars in them. Stars are not tiny objects. What could be responsible for pushing all of these galaxies apart from each other, right? We have no idea, which means that we have no idea whether it's going to turn around or whether it's going to continue or whether it's going to increase, right? But there's a fascinating consequence to it. The space between us and other galaxies is growing at faster than light can traverse that space. What does that mean? It means that these galaxies are going to move out beyond our visible horizon, right? So every year that you look up at the night sky, it's going to get darker and darker and darker. So imagine doing astrophysics in 10 billion years, right? If human civilization survives the next 3 years, right? Or until the next election. So imagine in 10 billion years we're trying to rebuild human astrophysics, right? And people are looking up into the sky and wondering, where is everything, right? Or is there anything out there? They could be looking up into a totally black sky, in which case they would have no clue about how things work. All the critical information that we learn from looking at the stars, they would be totally ignorant of. Now, before you feel like too great about the fact that we are living now, we can use the stars to help us understand the universe, remember, we're 14 billion years into the history of the universe already. If we had evolved 10 billion years ago and looked up at the night sky then, what would it have revealed to us that's now totally gone and lost forever? Well, we have no idea, right? So the future of the universe is something we don't understand, right? It's not something we can predict because we have no understanding of the mechanism by which the universe is expanding. And it's only recently that we've even understood that it is expanding, right? So that's why I say we're at a special moment in physics, because we've very recently figured out exactly how little we know about the universe, which means that we have an opportunity to learn something about it. Okay? So here's a pie chart to summarize our knowledge of the universe, right? Most of the universe is something we just don't understand at all, right? We label it with dark energy so we can write grants about it that sound cool, but really we have no clue what this thing is. There are some ideas. People come up with theoretical explanations for what dark energy might be, and they do calculations, and they compare those to what we see, and they're off by 10 to the 100. Okay? There's only like 10 to the 80 particles in the universe, so 10 to the 100 is a huge mistake. 27% of the universe is dark matter, something we know it's there, we know it's matter, we don't know really anything else about it. Is it one particle, is it lots of particles, is it something else totally weird? We don't know. The rest of the universe, this little corner, this 5%, the etc. part of the universe, that's me and you and ice cream and bicycles. Okay? We're really the little bits of the universe. And so you might think, well, how are we in making progress in understanding this question about what is the universe? So it's sort of like, imagine somebody told you to understand elephants, and you spent 300 years only studying the tail, not even realizing there was more to the story, right? And then one day, finally, somebody walks you around to the front like, excuse me, maybe you want to look at the rest of the elephant, right? Well, what are you going to do in that situation? How are you going to feel confident in understanding the rest of the elephant, right? Well, what you're probably going to do is say, well, maybe the rest of the elephant is made out of tails also, right? Or I can describe the elephant as a linear combination of tails that I already understand, right? Because you're going to cling to the theories you know, right? Well, you might think that's ridiculous. That's absurd. It's obviously a stupid thing to do. That's exactly the same argument I made 10 minutes ago about dark matter, right? Maybe dark matter is also made out of particles, right? Because that's all we know. So we should be careful in extrapolating our knowledge to the rest of the universe. It's a great tendency in physics to extrapolate from the known into the unknown, but it's also dangerous when you're extrapolating from an unrepresentative sliver. So I don't mean to be depressing. What I mean to do is to encourage you and to think about the kind of things we might be thinking about in the future, because this is a special moment in physics when you realize that you don't know very little. It's a chance you have to reboot, to throw away everything you thought you knew and think, you know what, maybe we're looking at an unrepresentative slice. We need to come up with some crazy new ideas, right? It's those moments when you know very little that give you the opportunity to totally come up with something completely new that could blow your mind, right? And in 200 years or in 500 years, children's books about the universe will contain facts that to us are crazy, that we wouldn't even believe, right? Imagine giving this talk to Isaac Newton, right? Staggering genius in the history of human physics. He had no idea about any of this stuff, and it would totally blow his mind. How can we take anything he said seriously, right? He had no clue about the cosmic situation. The way we think about primitive cavemen is the way future scientists will think about us. At least we know that we don't know very much about the universe, right? Which gives us a heads up or a way to get started. So we know that we don't know very much about the universe. However, it is an exciting time because at the same time as we know that we're clueless, we're also building awesome new tools to help us solve these mysteries. So we have the Large Hadron Collider, and it smashes particles together to try to see what's inside them. We have the gravitational wave observatories that can see ripples in space and time and black holes colliding billions of years ago, which is pretty awesome. We have space telescopes, which can help us look back into the early moments of the universe and figure out these questions about how things got started, right? What happened before the Big Bang. Hopefully in the future we'll have even cooler technologies, maybe given to us by our alien friends, right? I like to think that this is an amazing period in physics, that in the next 5 years or 10 years or 15 years, we will make some of these discoveries, answer some of these questions, and it will really be a turning point in the history of physics. I hope that in 100 years people think back and think, wow, I wish I had been a physicist back in 2020 when they really figured out whatever it is we're about to figure out, you know? I like to think about the discovery of quantum mechanics, right? All those experiments people did over like a course of 10 years or so, people just sat down and thought about it and figured it out and revealed what the true nature of the universe was. And I sometimes think, if I had been around then, I totally would have figured it out, right? But when you're standing at the forefront of human knowledge, right, not knowing which direction to go, any of these possible crazy ideas could be true, it's not easy to know which direction is correct, right? So in hindsight, it might be obvious, but here we are not knowing much about the universe. So to round out our tour of silly charts about the universe, and to impress on you how little we understand about the universe, right? This bit here is dark energy, right? Most of the universe is something totally not understandable to us, right? This bit here, dark matter, is something we're pretty sure it's matter, but that's about all we know. And this little bit is me, you, and dark chocolate. And so in our book, we talk about this one question: what is the universe made out of? Because it's one of these deep and ancient questions that we think can be answered and will be answered, and when it is, will change the way we think about the universe. But there are lots of these questions in science. Big, deep, ancient questions with answers, right? Questions like, what happened before the Big Bang, right? Nobody knows the answer to that question. Even the early moments of the Big Bang are still a mystery. Or even more basic questions like, what is space? You know, you might think, well, that's obvious. Space is emptiness, right? It's just the abstract backdrop on which things happen. Well, we know now that that's not true, because we know that space can expand. We know space can bend. Space can even ripple, okay? Emptiness cannot ripple. So space is not just emptiness. It's a thing that we live in. It's like as if we were fish and we've been swimming in water for thousands of years, not even realizing the water was a thing. We just thought it was, you know, the thing we're in, right? And then you discover, oh, it's a dynamical thing with properties, right? Space is like that. It might even have strange phases that we haven't even explored. We don't know basic things about space, like how many dimensions are there? Well, there's 3 that we're familiar with, right? But string theory predicts 11 or 26. And there's lots of ways that there could be extra little curled up loops of dimensions that we're not even familiar with. So really basic ancient questions about the universe have not been answered, but they have answers, right? These answers that can be revealed. So we talk about all of those in the book. And the point of our book and our presentation today is not to convince you that science doesn't know anything. It's to show you that science will make great discoveries in the future, and to prepare you for those by introducing you to our cosmic level of ignorance. So thanks very much for your attention.
So we're right up at the end of our allotted time, but I think we can take a couple of questions if anyone has any. And then afterwards, Daniel and Jorge have been kind enough to do a book signing.
And stick around and answer any other crazy questions you have.
Anyone?
No questions? Oh, here we go.
Are there some questions that you...
Just a moment.
Hi, thanks for giving us a great talk.
Thank
Are
you.
there any questions in this book that you would have liked to explore but did not manage to fit in the book?
Yeah, there are a lot of questions that we don't have the answer to that we also didn't talk about in the book. In the book, we tried to limit ourselves to questions that we thought people could understand without any scientific background, like simple, deep questions. For example, a lot of people ask us, why didn't you talk about the mysteries of neutrino oscillations in the book? Well, neutrinos are interesting, but it takes, it's like a 20-minute explanation for why they're interesting. So we try to focus on things that were very accessible. But there are other things like the mysteries of quantum mechanics. That would take a whole other book.
Cool. Thank you.
So stay tuned for our next book. we still have no idea.
Which ones are your favorites individually?
I think one of my favorites is the question of what is space, because it's not a question you hear a lot of people even ask, but I think it's a really deep and important question. I really liked writing that chapter because I like thinking about what space was. I first heard about like space expanding. I was like, what does that even mean? It's like, I understand each word individually, but together it's like, doesn't make any sense, right? So it's once you liberate yourself from the idea that space is an abstract idea and discover that it's a physical thing that you can think about how it changes and moves. It's a totally different way of thinking about the universe. That was my favorite one.
My favorite is chapter 13. If you get the book, it's a very special chapter. But no, there's also a chapter I really like called about cosmic rays. So, and I like it because it's a very, very specific mystery. Like like Daniel mentioned, we're being bombarded by particles all the time. And there are some, especially that are interesting because they're super, super high energy. Like they're super duper high energy. We're being shot at by these particles and nobody really knows where they're coming from or what could be making them. Like there's no process in nature or astrophysics or physics that scientists know about or could even imagine could be producing these super high energy particles. And so the possibilities are like insane. Like there could be some totally new thing in the universe nobody has ever seen before, or it could be like aliens shooting at us. So it's a pretty cool mystery.
Hi, thank you for the talk. Wasn't there a theory that our universe starts with the Big Bang, then crunches, and then Big Bang again? What happened to that theory if we're expanding now?
Great question, yeah. So there was a theory that sort of a cyclical universe, Big Bang, Big Crunch, Big Bang, Big Crunch, right? That theory is less popular now because of dark energy, because we know the universe is expanding like crazy. But we don't know what dark energy holds for the future. Dark energy, for example, only turned on about 5 billion years ago. So for a long time, the universe was just sort of coasting and slowing down, and then it turned on. What's going to happen in the future? It might turn around and make a big crunch. So a big crunch is still a possibility. In fact, there's a theory of space-time called loop quantum gravity that says that maybe all of space is pixelated on this tiny, tiny scale, and it specifically predicts a big crunch. So short answer is big crunch might still happen, but nowhere in the near future, so don't worry about it. And you still have to pay next year's taxes. But we know dark energy is such a mystery, we can't predict what's going to happen because we don't understand the mechanism for it at all.
Yeah, thanks for doing this talk. This is awesome. So I think it's super important to have entertaining, accessible examples of science, especially for like young people to get them interested in STEM and things like that. Are there other resources or organizations that you know of and that you support that you think are really good to point to or to support monetarily, other ways, things like that?
Well, first buy 10 copies of the book.
And give them to young kids or teenagers.
It's a good question. I agree that science communication is important, and in fact, it was Google that partially inspired this because I was reading, Google put out a science comic, a technical comic about the development of the Chrome browser. Scott McCloud did it. And like how to write a browser is not like going to be the top-selling story on the New York Times, but it was a really compelling comic. It was really well done in terms of communicating something technical. And so I'm seeing more and more of this like collaborations between scientists and artists. And I think not all scientists are good communicators, which is fine. You don't have to be good at everything. But the important thing is to pair up with somebody who's a good communicator and has artistic skills. And I hope to see more of that in the future. In terms of supporting those causes, that's a good question.
Yeah, there's a bunch of like YouTube channels that are really good at explaining science and things like that. And there's a lot of comic artists online doing it also. I think that what Daniel was saying that I agree with a lot is the idea that, I mean, you guys are the ones kind of making this technology and pushing the boundaries of science and engineering. And so I really like the idea of people in those positions kind of taking the initiative to not just do the research, but also think creatively and figure out new ways that to communicate this stuff out to people. I mean, there's a lot of examples now, but tomorrow somebody can come up with a totally different type of collaboration or way to communicate this stuff.
I saw a Higgs boson dance performance once. I'm not sure I learned much about science, but it was entertaining.
Hello. Are there
Hello.
any questions that you cannot conceive of a possible answer to? So, with dark energy, you could start making up theories tomorrow, and none of them would be particularly well founded. They'd likely be wrong. But it seems to me like you can conceive of what the answer might look like. Are there any questions where that's not true? So for me, one maybe is consciousness.
Right, so that's a great question. A lot of the times we can speculate, but our speculation exceeds the bounds of science. So one example is, what happened before the Big Bang? Well, it may be that all the information about what happened before the Big Bang was destroyed in the Big Bang, right? We'll never know. One popular theory of the Big Bang is that the Big Bang was one of many, and there's an infinite number of universes that were all created, but then now are separated from each other and are moving away from each other faster than the speed of light, so we will never detect them. That kind of theory is fun, but it's basically philosophy because you can't ever test it. So yeah, there are a lot of questions like what happened before the Big Bang where we can have ideas, but it's not clear we'll ever be able to test them. However, science is always moving forward, and things that used to be philosophy questions, right, are now science questions because we've developed new technologies and new ideas and new clever ways to test these subtle theories. That question you raised, what is consciousness, is sort of a favorite one of mine. It's one that I think will actually never be testable by science because science assumes consciousness, and so you can never step outside of it to probe that. But that's a whole other topic. Yeah, that's a great question.
Hi, thanks for the great talk. So I have a question about, so how do you think software engineers can contribute to perhaps answering some of these questions? And also, how do you see machine learning coming into the picture?
Wow, great question. We're doing a lot of machine learning these days in particle physics and in astronomy because we have larger and larger data sets and more subtle signals. So actually one of the things I personally research is how to use machine learning tools to solve particle physics problems. One thing you guys can do is hire more particle physicists. For example, Kanishka over here is one of my students, and he now works here at Google. To make more connections between these two fields, because you guys have a lot of awesome hammers, and I'm always frustrated when I see, for example, like, Facebook spent $100 million on this tool to identify somebody's face in a picture. It's like so much money is being spent on what seems to me like trivial problems, like, is there a cat in this internet video? So many PhD theses have been written on that question, right? Which is like a great example of like a hard question, but like, who cares, right? And we have hard questions where we actually care about the answer. What is dark matter? Is this a Higgs boson, yes or no, right? So just like talk to scientists, try to get them to explain their problem to you in terms of their language and teach them your language, and I think you'll find a lot of interesting overlap.
A cool project is, do you want to tell them about crayfish?
Yeah, so for example, one project I'm working on is trying to understand these cosmic rays by turning everybody's smartphone into a particle detector. And then if you network all of these smartphones together, you can build a global-sized telescope, which could look out into space and see maybe where these cosmic rays are coming from. It's called crayfish, cosmic rays found in smartphones. We certainly need software help for that project. So if you're really interested, send me an email. Do I think dark matter is more important than cats and videos?
Maybe dark matter is cats and videos.
Yeah, I think cats know something about dark matter they're not telling us.
Hi. It seems like every time we get closer and closer in getting an answer, it was like, oh, now we have dark matter, and then oh, now we have dark energy, and because now you have your pie chart of 5% is us, but I wouldn't be surprised like 50 years from now. Oh no, now we have another dark thing, so dark power or whatever. And now we know like
the dark side.
Yeah, so 0.1% of the universe. And so this is a question that I don't think has an answer. But do you expect that to continue happening, especially? Also the other way around. So now we have 3 particles, but I wouldn't be surprised that then we have 1, and then boom, a whole raft of infinite new particles, and we have a new table of fundamental particles, and we go like all the way rabbit hole upwards and downwards.
I love your question. We address this question specifically in the book. The question is like, could there ever be a theory of everything? Right? Could we ever understand the universe? So I hope not, because I like asking questions. But there are some arguments that the universe might have a smallest particle. So one way to interpret your question might be, could we ever drill down and discover the smallest particle, or is it just going to keep going forever, smaller and smaller and smaller particles, right? Well, we don't know. But there are some arguments that suggest that the universe has a distance scale beyond which you can't measure. The universe is pixelated at some smallest level, that there is an end to this. The arguments are pretty weak. They go like this. If I take all these numbers that I found about the universe, the speed of light, Planck's constant, Newton's gravitational constant, and I multiply them together in this creative way, I get a number that has units of distance. Okay? That's called the Planck length. What is that number? Well, it's 10 to the minus 35 meters. Really, really small. Does that mean the universe is pixelated? No. Does it mean if the universe is pixelated, it's pixelated at that size? No. But what do we do in science when we don't know what to do? We do the dumbest thing first. So that was the dumbest thing. So it's sort of a hand-wavy argument that maybe at that scale, or somewhere within a factor of 1,000,000 of that scale, the universe might be pixelated at the smallest level. But that scale is 10 to the 15 smaller than what we can currently see. So we're really far away from ever seeing that. I mean, you have to build like a solar system-sized particle collider to study things at that small scale. So I think it's likely that the universe is pixelated, though I don't have any hard evidence for it, and that eventually we can figure that out, but it's a long way from now.
Thank you.
Great question, though. I mean, even if we had the theory of everything, the questions don't stop, because you can ask like, why is there a 3 in that theory? What does that mean, right? Then philosophy takes over.
Hey, thank you for the talk. It was awesome.
Thank you.
Quick question. Don't you think the first person to see the Grand Canyon would have lived hundreds of thousands of years ago, not a few hundred?
Yeah, probably,
Yeah.
I mean, 10 or 20,000 years ago is the migration down from
But I have a science-related question, too. What do you think we're going to figure out first, dark matter and dark energy, or a unifying model of gravity and electromagnetism? Do we need one for the other? What do you think?
Well, that's a great question. We could figure out dark matter anytime in the next few years. It's possible. We're looking for dark matter very actively. We're trying to create it in the lab by smashing particles together. We have these big tanks of heavy water underground that are looking for dark matter. So we could discover it any moment, right? Or we could just keep looking for it and not find it. So dark matter is the most likely thing to be discovered in the next few years, but also could be decades. Dark energy, it's pretty exciting because it's such a big question. And we can make progress on that really unpredictably. It could be a long time. A unifying theory of gravity and the other forces, people have been working on that for decades and made very little progress. So I don't expect that to be wrapped up anytime soon. Unless we could visit a black hole and look inside of it, because inside a black hole is all the data we need to understand why we don't have a quantum theory of gravity. If you've seen the movie Interstellar, that part of that movie was actually true.
The rest? We have no idea.
We have no idea. Great question.
All right, well, I think we're going to wrap up the Q&A now, and then Daniel and Jorge will be signing books and answering any lingering questions for the next while. All
Thanks,
right,
everybody.
Yeah, thank you.
Thanks.